11 billion Earth-like planets orbiting Sun-like stars in our galaxy alone. Sounds promising for finding life, right? But here's the shocking truth that keeps astronomers up at night. We've discovered thousands of planetary systems across the cosmos, and not a single one looks like our solar system. Not one. Either we're witnessing the universe's greatest cosmic coincidence, or we're about to make a discovery that will fundamentally reshape our understanding of life's place in the cosmos. In the next year, data from a European satellite is going to settle this question once and for all, and the implications are staggering. By the end of this video, you'll understand why the rarity or abundance of solar system twins might be the most important astronomical question of our generation.
Let's start with what seems like great news. Over the past 3 decades, astronomers have confirmed the existence of roughly 6,000 planets orbiting other stars. We've learned something remarkable from this cosmic census. Essentially, every star you see in the night sky has planets. Planetary systems aren't rare cosmic accidents. They're the default state of stellar evolution. This discovery alone would have seemed like science fiction just 40 years ago. But as we've built up this catalog of alien worlds, a strange pattern has emerged that nobody predicted. The vast majority of planetary systems we've discovered look nothing like our home. Our solar system features a distinctive architecture: small rocky planets close to the sun, with massive gas giants occupying the outer reaches. Mercury, Venus, Earth, and Mars cluster in the inner system, while Jupiter, Saturn, Uranus, and Neptune dominate the outer solar system. This arrangement seems natural to us because it's all we knew for most of human history.
However, the exoplanet revolution revealed something unsettling. Most planetary systems don't organize themselves this way at all. Instead, they follow what astronomers now call the peas-in-a-pod configuration. In these systems, planets tend to be similar in size and mass regardless of their distance from their star. You might have heard of TRAPPIST-1, a system featuring 7 roughly Earth-sized planets all orbiting close to a red dwarf star. This isn't an outlier. It's actually closer to the cosmic norm.
The most common planetary systems we've found consist of chains of super-Earths, or mini-Neptunes. These are worlds larger than Earth, but smaller than Neptune, arranged in tight orbits around their stars. Some systems have multiple gas giants, all clustered close together. Others have uniform rocky planets spread throughout. But that distinctive split we see in our solar system, with terrestrials inside and gas giants outside, appears to be genuinely unusual.
This raises a profound question. If 11 billion Earth-sized planets exist in habitable zones around sun-like stars in our galaxy, why don't we see them arranged in solar system-like configurations? Why are they typically found in these uniform chains instead? And, most importantly, does the unique architecture of our solar system have anything to do with the emergence of life on Earth? To understand why this matters for life, we need to talk about Jupiter's possible role in Earth's biological history. There's a compelling hypothesis that Jupiter acted as Earth's cosmic guardian during the critical early period when life was first emerging. Picture the early solar system as a chaotic shooting gallery. Comets and asteroids were far more numerous than today, and collision events were frequent and devastating. Some of these impacts delivered water and organic molecules to Earth, which might have been beneficial. But too many large impacts would have repeatedly sterilized our planet's surface, preventing life from gaining a foothold. Enter Jupiter, the solar system's massive bouncer. With the mass more than 300 times that of Earth, Jupiter's gravity is powerful enough
to significantly alter the trajectories of incoming objects. Some get captured into orbit around Jupiter itself. Others get deflected out of the inner solar system entirely, or even ejected from the solar system altogether. Still others have their orbits changed in ways that make them less likely to strike Earth. The question is whether this protective effect was necessary for life to develop on our world.
This hypothesis is still debated among planetary scientists, and the truth is we don't have a definitive answer yet. The early bombardment history of Earth is difficult to reconstruct because geological processes have erased most of the evidence. We can study impact craters on the Moon to infer Earth's bombardment history, but even lunar geology has gaps. Some scientists argue that Jupiter's protection was essential, allowing life the breathing room it needed to evolve. Others contend that life is remarkably resilient and would have emerged regardless, perhaps even benefiting from the delivery of organic compounds via impacts.
But here's what makes this question so urgent. We can't answer it by studying our solar system alone. We need a comparison set. We need to find other systems with both Earth-like planets in habitable zones and Jupiter-like giants in outer orbits. Then we need to determine whether those Earth analogs show any signs of life, or at least conditions favorable to life. If we consistently find that Earth-Jupiter configurations correlate with biosignatures, that would be powerful evidence that our solar system's architecture isn't just unusual, it's special in a way that matters for life.
The problem is, until very recently, we haven't found any such systems. Not a single confirmed example of a Sun-like star hosting both a habitable Earth analog and a Jupiter analog in a Jupiter-like orbit. This brings us to a critical question. Is this absence real, or is it just a limitation of our detection methods?
Understanding why we haven't found solar system twins requires understanding how we find exoplanets in the first place. Each detection method has strengths and weaknesses, and these biases shape what we see when we survey the cosmos.
The first wave of exoplanet discoveries came from the radial velocity method, also called the Doppler method. This technique exploits a subtle fact about orbital mechanics. Planets don't actually orbit stars. Rather, both star and planet orbit their mutual center of mass, called the barycenter. Because the star is so much more massive than its planets, this barycenter lies very close to the star's center, sometimes even inside the star itself. But it's not exactly at the star's center, which means the star wobbles slightly as planets tug it around. This wobble reveals itself through the Doppler effect. As the star moves toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, the light shifts toward red. By measuring these shifts with high-precision spectrometers, astronomers can detect the presence of planets and determine their masses and orbital periods. This method was tremendously successful in the late 90s and early 2000s, revealing dozens and then hundreds of exoplanets.
But radial velocity has significant biases. It's most sensitive to massive planets in close orbits. A massive planet pulls its star harder, creating a larger wobble, and thus a bigger Doppler signal. A close-in planet completes orbits quickly, making the wobble faster and easier to detect in a reasonable observation timeframe. This combination meant the first exoplanets discovered were hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our Sun. These worlds were completely unexpected and forced astronomers to rethink theories of planetary formation.
The launch of the Kepler Space Telescope in 2009 initiated the transit method era. Kepler stared continuously at one patch of sky containing about 150,000 stars, measuring their brightness with extraordinary precision. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light, causing a brief, repeating dimming event. By catching 3 or more of these transits, astronomers can confirm a planet's existence and determine its size and orbital period.
Kepler revolutionized exoplanet science, eventually contributing thousands of confirmed planets to our catalogs. The transit method could detect smaller planets than radial velocity, including Earth-sized worlds. This finally gave us hard data suggesting that terrestrial planets are common throughout the galaxy. Kepler discovered several Earth-sized planets in habitable zones, particularly around red dwarf stars, though also around a few sun-like stars.
But the transit method has its own limitations. Most critically, it only works for planetary systems aligned edge-on to our line of sight. If a planetary system is tilted, its planets won't pass in front of their star from our perspective, and we'll never detect them through transits. This geometric requirement means the transit method can only find a small fraction of existing planets. Additionally, transit detection requires observing multiple transits, which means multiple complete orbits. For a planet in an Earth-like orbit, that means at least 3 years of continuous observation just to get 3 data points. Here's where the Jupiter problem becomes acute. Jupiter takes 12 years to complete one orbit of the Sun. If we wanted to detect an exojupiter using the transit method, we'd need to observe its star continuously for at least 36 years to catch 3 transits. Kepler operated for only 4 years in its prime mission. The TESS satellite that followed Kepler scans most regions of sky for less than a month at a time. These missions simply aren't designed to find distant gas giants, even though those planets are enormously important for understanding planetary system architecture. The radial velocity method can detect Jupiter-like planets without waiting for a full orbit, because the Doppler signal starts accumulating immediately, and the orbital period can be inferred from partial data. However, radial velocity surveys can only monitor a limited number of stars at once, so they're not ideal for the initial discovery phase, where you're trying to identify which of thousands of candidate stars actually host planets. What we really need is a detection method that can survey many stars simultaneously, detect planets in wide orbits without waiting decades, and work regardless of the planetary system's orientation. That's where astrometry enters the story. Astrometry is simply the science of precisely measuring positions in the sky. It's one of astronomy's oldest disciplines. Ancient astronomers practiced astrometry when they cataloged star positions to track celestial motion and predict eclipses. But modern astrometry operates at a level of precision that would seem like magic to ancient observers. Here's the key insight. If we can measure stellar positions with sufficient accuracy, we can directly observe the wobble that planets induce in their parent stars. Remember that stars and planets orbit their mutual center of mass. For most of the 20th century, this wobble was far too small to detect for planet-sized companions. But advances in telescope technology, and particularly in space-based observations, have made astrometric detection of exoplanets possible. The beauty of astrometry for planet hunting lies in its unique sensitivity profile. Radial velocity and transit methods favor close-in planets. Astrometry favors distant planets. Why? Because the location of the barycenter depends not just on the planet's mass, but also on its distance from the star. A planet in a wide orbit pulls the barycenter farther from the star's center than a close-in planet of the same mass. This creates a larger wobble in the star's apparent position on the sky. There's another crucial advantage. Unlike transit searches, astrometric works for planetary systems with any orientation relative to our line of sight. You don't need the lucky geometry of an edge-on system. And unlike radial velocity monitoring,
Astrometric surveys can observe thousands of stars simultaneously, building up positional measurements over time for massive samples.
The catch is that astrometry requires extraordinary precision. The wobble induced by a Jupiter-like planet on a Sun-like star at interstellar distances is incredibly tiny. To detect it, you need to measure stellar positions to accuracies measured in micro-arcseconds. To put that in perspective, 1 micro-arcsecond is the apparent size of a period on a page viewed from 1,000 kilometers away. It's about the width of a human hair is seen from the distance between Earth and the Moon. Achieving this precision from the ground is essentially impossible due to atmospheric distortion. You need to go to space.
This is where the Gaia mission enters our story. Launched by the European Space Agency in 2013, Gaia spent over a decade creating the most detailed three-dimensional map of our galaxy ever made. The satellite orbits the Sun at a point called L2, about 1.5 million kilometers from Earth, in the direction opposite the Sun. From this vantage point, Gaia continuously scanned the entire sky, repeatedly measuring the positions of over 1 billion stars.
Gaia achieves its remarkable precision through an elegant design. It carries 2 telescopes mounted on a single rigid platform that slowly rotates. The spacecraft converts the problem of measuring stellar positions into the problem of measuring time intervals. Specifically, it measures the exact moment when a star crosses through the field of view of each telescope. By combining dozens of these timing measurements taken over years, Gaia can determine stellar positions with extraordinary accuracy. The real test of any exoplanet detection method is whether it actually finds planets. For Gaia, that confirmation came with the discovery of Gaia-4b and Gaia-5b, announced following analysis of the mission's 3rd data release in 2023. These worlds are super Jupiters, meaning they're significantly more massive than Jupiter itself. Gaia-4b weighs in at 12 Jupiter masses, while Gaia-5b contains 21 times Jupiter's mass. Both orbit relatively small, low-mass stars. What makes these discoveries scientifically valuable, beyond just being first, is that they represent a population of planets that other methods struggle to find. Super Jupiters orbiting low-mass stars were thought to be extremely rare based on radial velocity and transit surveys. The physics of planet formation in disks around small stars suggests that building such massive planets should be difficult. The disk simply might not contain enough material, and the timescale for giant planet formation might exceed the lifetime of the disk.
Yet, here they are. Gaia found them because their combination of high mass and wide orbit creates substantial stellar wobbles that astrometry can detect. The fact that the very first dedicated analysis of Gaia data for exoplanets turned up these surprising objects tells us something important. We've been operating under incomplete information about the diversity of planetary systems. Our census has been heavily biased towards certain types of planets and certain types of systems. There's a whole population of worlds out there that we simply haven't been able to see until now.
The process of confirming Gaia-4b and Gaia-5b illustrates both the power and the challenge of astrometric planet detection. First, astronomers had to sift through Gaia's measurements of hundreds of millions of stars, looking for the specific signature of orbital motion. Not every wobble indicates a planet. Binary star systems create much larger wobbles. Measurement uncertainties can mimic wobbles where none exist. External gravitational perturbations from passing stars or giant molecular clouds can affect stellar positions. Once candidates are identified, follow-up observations become essential. Radial velocity measurements can confirm that the wobble is real and refine the planet's properties. The combination of astrometric and radial velocity data together provides the most complete picture of a planet's orbit and mass. This synergy between different detection methods represents the future of exoplanet characterization. Now we arrive at the exciting part, the reason this topic matters right now. Gaia-4b and Gaia-5b are just the beginning, a tiny preview of what's coming. Gaia's fourth data release, scheduled for December 2026, will transform exoplanet science.
Data Release 4 will be fundamentally different from previous releases in a critical way. For the first time, it will include Gaia's complete time series astrometric measurements rather than just derived parameters like parallax. This means astronomers will have access to the raw positional data spanning 5.5 years of observations, roughly twice the baseline of the third data release. This extended timeline is crucial because it makes Gaia sensitive to planets with longer orbital periods. Remember, astrometry detects the orbit playing out in real time. More years of data means sensitivity to planets farther from their stars.
Recent theoretical work by astrophysicists Caleb Lammers and Josh Wynn has estimated what we can expect from this data release. Using sophisticated simulations that model Gaia's capabilities and account for the actual distribution of stars and planets in the galaxy, they predict Data Release 4 will lead to approximately 7,500 exoplanet detections. Let that sink in. The currently confirmed exoplanet count stands at roughly 6,000 worlds. Gaia is poised to more than double that number in a single data release.
But even that extraordinary figure pales compared to what's coming later. Gaia continued collecting data until March of this year, giving it a total mission span of over 10 years. The full dataset, Data Release 5, is planned for the early 2030s. Lammers and Wynn predict this complete dataset will yield approximately 120,000 planet detections. That's a 20-fold increase over the current census. That's not just quantitative growth, it's qualitative transformation.
Why such a dramatic increase from Data Release 4 to Data Release 5? Two factors drive this explosion in discoveries. First, the longer observational baseline continues to extend Gaia's sensitivity to longer period planets. A 10-year dataset can detect planets that take several years to orbit, capturing populations that 5-year data simply misses. Second, and perhaps more importantly, planets with longer periods have larger physical orbits, and larger orbits mean larger stellar wobbles. This means these planets can be detected at greater distances from Earth, dramatically expanding the volume of space Gaia can effectively survey for planets.
The types of planets Gaia will find are particularly exciting for the solar system analog question. Gaia will be sensitive to Jupiter mass and super-Jupiter planets in orbits ranging from about 1 to 5 astronomical units from their stars. Jupiter itself orbits at 5 astronomical units, so Gaia should be able to detect genuine Jupiter analogs. It won't be sensitive enough to detect the tiny wobbles induced by Earth mass planets, but that's acceptable because that's what transit missions like Kepler and TESS are designed to find. This brings us to the beautiful synergy emerging in exoplanet science. Different detection methods have complementary strengths and weaknesses. Transit missions excel at finding close-in planets, including small terrestrial worlds in habitable zones. Radial velocity can detect planets of intermediate orbital distances. Astrometry specializes in distant giant planets. By combining data from all three methods, we can build comprehensive pictures of complete planetary systems. Here's the game-changing possibility. Gaia will identify thousands of stars hosting Jupiter-like planets in Jupiter-like orbits. Some of those same stars will have been observed by Kepler or TESS, missions that searched for interterrestrial planets via transits. For the first time, we'll be able to identify systems that have both components, Earth-like worlds in habitable zones and Jupiter-like giants in outer orbits.
These are solar system analogs, the cosmic twins we've been searching for.
If we find many such systems, it would suggest our solar system's architecture isn't particularly special. The combination of inner terrestrials and outer giants might be a common outcome of planetary formation under certain conditions. This would be scientifically fascinating, teaching us about the dynamics of protoplanetary disks and the processes that sort planets by composition. But it might complicate arguments that Jupiter's presence was necessary for life on Earth. If many Jupiter plus Earth systems exist, we'd need to explain why we haven't detected biosignatures in any of them yet.
Alternatively, if we find that solar system analogs are genuinely rare, even in Gaia's massive data set, that would support the idea that something unusual happened during our solar system's formation. The Grand Tack hypothesis, which proposes that Jupiter migrated inward through the early solar system before reversing course and retreating outward, offers one explanation. This migration would have disrupted the formation of planets in the inner system, scattering much of the material and leaving behind a depleted region. The terrestrial planets then assembled from the remnants. If this migration resulted from an unlikely gravitational interaction, perhaps involving a close encounter with another star during the Sun's time in its birth cluster, it could explain our system's rarity.
The implications extend to the search for life. If solar system analogs are rare, and if Jupiter's presence was indeed important for life's emergence on Earth, then we might need to revise our estimates of how common life is in the universe. Those 11 billion Earth-sized planets in habitable zones start to look less promising if most lack the protective Jupiter-like companion that might be necessary for complex life to evolve. This doesn't mean life is rare overall. Life might find other pathways we haven't considered, but it would suggest that life as complex as Earth's biosphere might require a more specific set of circumstances than we've assumed.
The scientific value of Gaia's upcoming data releases extends far beyond simply counting planets. Each detection provides rich information about planetary system architecture and evolution. By measuring the masses, orbital distances, and eccentricities of thousands of giant planets, astronomers will be able to test theories of planet formation in unprecedented detail.
One major question Gaia will help answer is how giant planets actually form. Two competing theories have long divided the planetary science community. The core accretion model proposes that giant planets begin like terrestrial worlds, with solid cores building up through collisions of smaller objects in the protoplanetary disk. Once a core reaches sufficient mass, its gravity becomes strong enough to rapidly accrete massive atmospheres of hydrogen and helium gas. The gravitational instability model, instead, suggests that giant planets form more like stars, with regions of the protoplanetary disk becoming gravitationally unstable and collapsing directly into planet mass objects.
These formation mechanisms make different predictions about where giant planets should be found and what their properties should be. Core accretion predicts that giant planets should form beyond a certain distance from their star, called the ice line, where temperatures are cool enough for ices to condense. Gravitational instability can operate at various distances but requires massive extended disks. By mapping the statistical distribution of giant planet properties, Gaia will provide evidence favoring one mechanism or the other, or perhaps revealing that both operate under different circumstances.
The question of planetary migration will also come into focus. Many of the hot Jupiters discovered by early surveys couldn't have formed where we find them. The protoplanetary disk is too hot and depleted close to the star for giant planets to assemble in situ. Instead, these planets must have formed farther out and then spiraled inward through interaction with the disk or through gravitational interactions with other planets.
Understanding how common this migration is and what determines whether a giant planet migrates inward or stays in a wide orbit is crucial for understanding why our solar system looks the way it does.
Gaia's data will also illuminate the relationship between stellar properties and planetary systems. Do sun-like stars preferentially host certain planetary architectures? Are solar system analogs more common around stars of particular masses or metallicities? Do binary star systems have different planetary demographics than single stars? These connections between stars and their planets will emerge from statistical analyses of Gaia's massive sample.
Perhaps most intriguingly, Gaia might reveal correlations we haven't even thought to look for. With 120,000 planets in the final dataset, patterns and relationships that would be invisible in smaller samples will become apparent. The history of astronomy is full of examples where large datasets revealed unexpected phenomena. The Sloan Digital Sky Survey transformed our understanding of galaxy evolution, not just through planned analyses, but through serendipitous discoveries that nobody anticipated.
It's worth stepping back to appreciate how far we've come. Just 33 years ago, in 1992, the first confirmed exoplanets were discovered orbiting a pulsar. These dead star systems bore no resemblance to our solar system and told us nothing about whether solar system-like planets were common. The first planets around sun-like stars came later in the 90s, strange hot Jupiters that challenged everything we thought we knew about planetary systems.
For a period in the late 90s and early 2000s, it genuinely seemed possible that our solar system was an oddball, perhaps even unique. The planetary systems we were finding looked nothing like home. But as our detection methods improved and our surveys expanded, we realized we were simply seeing the easiest to detect planets first. Planets like Earth, in Earth-like orbits, are intrinsically difficult to find. The absence of evidence wasn't evidence of absence.
Kepler changed that, revealing that terrestrial planets are not just common, but probably the most abundant type of planet in the galaxy. Nearly every star has planets, and many of those planets are roughly Earth-sized. But Kepler also revealed the puzzling peas-in-a-pod phenomenon, suggesting that uniform planetary systems might be the norm. We moved from thinking Earth-like planets are rare to knowing they're common, but wondering if solar system-like arrangements are rare.
Now we stand at another threshold. Gaia is about to tell us whether the full solar system architecture, inner terrestrials plus outer giants, is common or genuinely unusual. This knowledge will fundamentally inform our search for life and our understanding of our place in the cosmos. If solar system twins are abundant, the next generation of telescopes might detect biosignatures in their atmospheres within decades. If such systems are rare, we might be truly special in ways we're only beginning to understand.
The timing is remarkable. The James Webb Space Telescope is now operational, capable of analyzing exoplanet atmospheres for biosignature gases. Future missions like the Habitable Worlds Observatory are being designed specifically to directly image Earth-like planets and search for signs of life. But these efforts need targets, and not just any targets. They need to know which systems are most likely to host life. Gaia's census of Jupiter analogs, combined with Kepler and test data on inner planets, will provide exactly that target list. So where does this leave us? Within the next 2 years, Gaia Data Release 4 will begin answering one of the most profound questions in astronomy. Are we alone in our cosmic architecture, or are there countless solar system twins scattered throughout the galaxy? The answer will reshape how we think about planetary formation, the requirements for life, and the likelihood that we'll someday detect biosignatures in another world's atmosphere.
If we find that our configuration is common, it suggests that the physical processes that built our solar system are robust and repeatable. The combination of terrestrial worlds in warm, close orbits and giant planets farther out might be a natural outcome of how planetary systems assemble. This would be encouraging for the search for life because it would mean many stars host environments similar to the one where life emerged on Earth.
If instead we find that solar system analogs are genuinely rare, we'll need to understand why. What made our system special? Was it truly the Grand Tack migration, or something else entirely? And critically, was that special circumstance necessary for life to evolve, or was it merely incidental? These questions won't be fully answered by Gaia alone, but Gaia will frame them in ways we couldn't before. What's certain is that we're living through a golden age of exoplanet science. Every year brings new discoveries, new techniques, and new insights. The combination of different detection methods, from transits to radial velocities to astrometry, is giving us an increasingly complete picture of the diversity of worlds in our galaxy. And that diversity is staggering. Hot Jupiters that orbit their stars in days, super-Earths that have no analog in our solar system, ice giants, lava worlds, ocean planets, and things we don't even have names for yet.
But amid all this diversity, we keep looking for home. Not Earth itself, but systems, like the one that gave rise to Earth. Systems where life might emerge, evolve, and perhaps eventually develop technology and wonder about its place in the cosmos. Gaia is about to tell us how many such places might exist. The implications will ripple through astronomy, biology, and even philosophy as we grapple with what it means if we're either common or rare in the cosmic landscape. Whatever the answer, our understanding of our place among the stars is about to change forever.